All right, we're going to process some of the data that we built in the previous video. We're going to go in and do a Zipf's law calculation. It's not normally done, but it's a good starting place. I've made a few changes since into the download file, a couple of errors I found. There was an error allowing capital letters from the first line of an abstract into the result. It didn't ruin things catastrophically because there were very tiny numbers of them. But it's been fixed, and I just found another error in one of the programs. Minor error. It did not cause the thing not to work. But anyway, you may see some differences. If you get the older version, I'll update everything as I find the errors. First of all, let's go into index.script, which is where we were, and we go down to the Zipf's law. This is where we were. We've come down here. We've got OSU.converted is what that is. And we did look at OSU.converted. Let's look at it again in case you've forgotten. OSU converted looks like that. Each document or each abstract has been reduced to a big giant long line. Okay? All the words are lowercase, all the punctuation's gone. They're just words. The first two items on each line is, first of all, the offset in the original file of where the abstract was, and the second one is the document number, simple number 1, 2, 3, 4. So you can see those two numbers at the beginning. Everything else just one big giant long line. So that's OSU converted. So it's been done. We won't be doing it again. We'll go back to index.script. And it's around line 113. I've already modified here, excuse me. I did a modification and I didn't change it. This is what the line actually looks like. Yours will have a pound sign in front here. Yours will look like that. So you need to remove the pound sign if you want to run this. Normally I don't run this. It's just of interest. It's not really part of the larger calculations. Remove the pound sign. Now it will run. I put an exit in here so when it's finished running, the program will terminate. It won't go any further. Okay, what are we doing? First of all, we're running the Linux program head, Unix program head. It is a program in all Unix distributions, Linux distributions, and what it does is it writes out the first so many lines from a file. By default, the first 10 lines. If you don't want it to be 10 lines, you have to tell it how many lines. Maxdocs is the number that you give when you invoke this script. So if you say index.script space 1000, maxdocs will be 1000. The $ means don't put the word maxdocs here, put its value. Okay, that's bash. $ in front of it makes the value appear, not the actual word. Second part, so that is the number of lines to show. Remember, each line is an abstract. All right, then we go to the next one here, $db.converted. $db is OSU for us, and so that's the file. That's the input file. The output of head normally goes to standard out, which is normally your screen. Instead, we're grabbing it and we're piping it. We're sending it on to the next program. The next program reads from standard in, normally your keyboard. However, when you pipe something to it, it doesn't take it from your keyboard, it takes it from what's being sent to it. So the output of the head program is going into wordlist.mumps. Pretty standard thing that you do in Linux. All these programs can be running simultaneously, unless there's some reason why one of them must wait until the previous one stops. They will, head and wordlist will be running concurrently, and if you've got a multi-core CPU, which most people do nowadays, it'll use both CPUs, and it does make it run more efficiently. You could do these as separate steps, of course, but that's the reason for piping things. Okay, wordlist.mumps is going to write out all the words, one word per line. Not going to write out the numbers, it's going to write out the words. Going to write out the words, one word per line. The output goes to standard out, which is being grabbed and piped to the sort program. Sort program is built into Linux. It sorts things. It sorts them alphabetically if you don't tell it to do anything else. So the words coming out of wordlist.mumps are going to get sorted alphabetically. Now, in the file, if there's 100 instances of the word in the sorted version, which is going to be piped to unique, in the sorted version, all of the instances of the word the will appear on consecutive lines. There'll be 100 lines with the word the on it, and all the other words will, unless a word only occurs once, then it'll be only on one line. All right, unique goes through and finds out how many unique instances and counts them, how many unique instances of each word there is, or the values on a line, really. But so it's going to write out a count. So instead of seeing 100 lines of the, we're going to see one line of the preceded by the number of times the word the appeared. So it's a counting program. It's very fast, very efficient. Okay, the output of unique, which is going to be a number and a word on a line. It's the number of times the word appears in the collection as a whole. That's what you're finding out. We're passing it back to sort, another instance of sort. This time, sort is going to sort numerically. Sort normally sorts alphabetically, but since the first item on the line, and if you don't tell it anything different, it sorts according to the first field, where field is delimited by white space. So the first field, in this case, is going to be the number, is going to be the thing that's the basis of the sort of the file. Now, we want it to do a numeric sort, not an alphabetic sort, so we say -n. The R means that we're going to do it in reverse order. So the result is going to be from high to low. The most frequent number will be first, and the least frequent will be last. And then we pipe that to a program called Zipf.mumps, which does some other stuff. Needs to know the number of documents, and it writes it out to the final thing. The greater than sign means redirection. The output, which would normally come to your screen, is instead going to go into a file. Since there's going to be a lot of output, we don't want to see it flashing by. All right, so that's how it works. Let's just look at parts of it. And this is where I'm short-circuiting. You saw that when I went in here. Whoops, I meant to put the pound sign there. So this line here you see is just the remainder of the line, but it's a comment, so it won't be executed. And I'll get rid of that because we don't want that. So just run that portion of it and see what happens. Okay, if I say index.script, and we'll just use a small number like 500. Now we're not going to do the conversion because it'll see that the converted files already exist. We're not going there again. There they are. There's the words coming right at us as predicted. Let's look at word list.mumps. What does it do? It's a very simple program. I just found a couple of tiny errors in it. That's why it shows today's modification. Today is February the 8th. Forever. Notice the 2 blanks after 4. Set I equal to $ZZ input, parenthesis, quote, W, quote. That's one of my functions. It's one of my input functions. A little weird. What it does is it will create a local array called W, and it will put into the elements of W the words that it finds on the input line. So if there's 1,000 words on the input line, there will be 1,000 elements of the array W, which will be created. All right, the I coming back is the total number of elements in the array. So it'll vary each time we call it. So in this case, if there's 1,000 words on the line, I will come back 1,000. If I comes back 0, it's over, we're done. I decrement I by 1 because the array W goes from 0 to, say if I had 100 words, it'd go from 0 to 99. The last, there's 100, value of I is 100, but the last element is not element 100, it's element 99. So that's the last element I'm going to process. And then I process them here, where J goes from 2 by 1 up to I. All we do is write out the words and a new line character. We start at 2 because we don't want words 0 and 1. Those aren't really words, they're numbers. Those are the offset and the document number. So that's what we saw. That's what we saw coming out. We saw the words coming out from the first 500 documents, and there were quite a few of them. You could actually find out by, well, let's not find out. Let's go back up and go to index, and let's move on from there. Let's see, it's about line 113. There we are. Let's get some of this back together again. So here's the sort. Let's cut it off. Let me go up here and put the pound sign in there. So now we're going to see the sort. Let's run it again. Now, of course, it scrolled by. Hyphens, by the way, are not pulled out. They're left in. That's one of the punctuation. You can see the words, how many times the word words appear, how many times the word woman appeared, and so forth. Some of these words like with, look how many, I'm scrolling, you can't even see it, this huge number of instances of the word with. It's very popular, apparently. And were, you expect these to be there many times, of course. Anyway, that's the That's the raw result there of words sorted so that all the words that are the same are together. Now let's go back in and we go back down here and we'll close that up. And now let's see what the unique gives us. Oops. So the output, now we're going to see the output of unique. Because I'm cutting off the piping, and so instead it will default coming back to the screen. All right. Well, again, you notice they're alphabetic because the words were originally alphabetic, but we see in front of each one a number. And that is the number of times. It says that visual occurred 36 times. It said that ventricular occurred 49 times. It's interesting because this is a medical database, and you'd expect words like ventricular to occur a lot. If you were looking at a database on, I don't know, computer science or chemistry, and you saw the word ventricular, it would be very odd, and it would stand out. So let's see. It's what you expect. Some of them are quite like the word two appeared 84 times and so forth. Okay, let's go back in. And we'll short circuit that. Now we're going to do now we're going to see the output of the sort. We're going to see the output of the numeric sort of all this. Now, okay, just run it. Now, it was reversed order, so all of the words that occurred once are down here. Let me have to scroll way back up there to get words that occurred twice. Some of these words are pretty rare, and you see the numbers are rising because at the beginning, let me run this again, and I will pipe the output to more, so we'll see the front of it. There we go. Not surprising, the word the occurred the most, 1,447 times. With is 831 times. This is what you would expect, right? Okay. Now, let's go back in to our program and join those up again, get rid of the pound sign. Now we are going to the last one, so I won't do anything else. We're going to look at Zipf.mumps. Zipf.mumps. First of all, it asks whether or not a parameter was provided. Hopefully a parameter was provided here. And the number of documents. The $ data on %1, if it doesn't exist, we default to 1,000 documents. That would change the results quite a would change the results, but this the number of documents is the parameter, and if it's if you don't give it, it just defaults to 1,000, which was pretty much what we're going to use anyway. Otherwise, we set, so in other words, if it doesn't exist, we set d equal to 1,000. If it did exist, this is the else case, we set d equal to the value of %1. Remember, in Mumps, % is a legal character to begin a variable name with. And the way my version of Mumps is set up, this will vary in other versions, but in my version of Mumps, the command line parameters are $0, that's the name of the program, $1, $2, and so forth, if they exist. Okay, we write out a nice little header giving the date in normal format, giving the day of the week, the month, and all that stuff. A title. What is Zipf? Zipf is the rank times the frequency of the rank of a word times its frequency. What's the rank of a word? Well, is it the first most frequently occurring, the second most frequently occurring, the third most frequent? It's the rank in terms of its frequency of occurrence. So if a word is 20th most frequently occurring word in a collection, its rank is 20. The frequency is the total number of times the word occurs in the collection. The concept of Zipf's law, and this actually works in a number of different areas besides information retrieval, is that the product of the rank and the frequency is approximately a constant. It's not, it varies a little bit, but it's remarkably so. It is largely a constant. Now, the number is quite large. In a large data set, frequency times rank can give you very large numbers. So we divide it by something. because it's not a really precise value. We don't care about it from more than about 2 or 3 places of accuracy, tops. So I divide it by the total number of documents, and that gives us a more manageable term. All right, and let's see. Let's look at the program here. For I equals 1 by 1, do. Now here I didn't say do forever because I is going to be the rank. As I read the document, I read the lines in, the first line, second line, third line, those are the ranks. Those are the ranks of the actual words. So I is going to be the rank. So I read a line in, I see if we ran out of lines, if $sign test is false, we're out of here. Break. I remove all the extraneous blanks. Now, if you remember from the output there of unique, there were a lot of blanks at the beginning, a lot of blanks all over the place. $Z blanks in my version of Mumps removes extra blanks. If it sees 2 blanks, it replaces them with 1. If it sees 3 blanks, it replaces them with 1. So extra blanks have gone. Okay, because that makes the piece function work better here. So I'm looking for the first piece on the line, which is the frequency. And I'm looking for the word, which is the second piece on the line, where piece is determined by a blank. So on the lines that are after they've been processed by Z blanks, there's going to be a number, a blank, and a word on the line. This pulls off the number, this pulls off the word. And then I set T equal to I, which is the rank, that's the index of the loop, times F, which is the frequency, that's the part we got off the line itself, divided by D, just to make it more manageable. That's it. So we write it out using justify. T is the value we're writing out in a field of 6 with no decimal places. I do not want to see an infinite number of decimal places here. It's not meaningful. We just roughly want to see the numbers to see if it's working and see if there's anything odd. A blank, the word, and a new line. All right, so now we go back to index.script, and let's give it a large number of documents, like 20,000. The larger the number of documents, the more likely it's going to be a smoother number with less jaggedness in it, less variability. If I do a really, really large number, it becomes more uniform. You don't get little isolated pockets. There might have been one article in there that used one word really a lot. But if you looked at a much larger number of articles, that would sort of blend out. It was just a little bit of noise. Anyway, it's running. And it doesn't take too long, but it's grinding away. There it is. All right. The result is, whoops, zipflaw.text. And at the top here, we're going to get a lot of variation. The most frequent word is the word the, and its Zipf coefficient is 3. That's some fractional part, but I don't care about it. And as we look there, it rises a little bit. As I go down here, you see the numbers are, they're not completely alike. 114 seems to be really popular, but as we go further and further into the file here, the numbers are really approximately the same. They vary a little bit. Again, if I did a larger sample, it would, as you get down here, it's going to get a little bit more variable, because these are very infrequently occurring words that are, what line am I on, for example? I'm on line 15,862, so I'm on the 15,862nd word in the collection. So we're really down there in terms of the vocabulary. Normal vocabularies are only a couple of thousand words for most people. Of course, this is a medical text. It's going to have an awful lot of extra words in it, like histochemically. That's not something we throw around in daily conversation. But it's seeing them. And the number is holding out. So that's Zipf's law calculation. And it is part of the basis of understanding information retrieval is that words, usage of words is somewhat predictable, and where it goes off that predictability, when we start seeing an article with clumped usage, we saw an article that used the word ventricular a great deal, much more than would be expected in the collection as a whole. That tells us this article is probably deals with ventricular or something related to it. So this is one of the, it's been around a very long time. People started doing these calculations back in the 50s. But anyway, that's Zipf's law, and you saw how we pipe programs, the output of one program becomes the input of another program, and we'll do quite a bit of that. In places we'll have several programs running simultaneously, and that if you've got a multi-core processor, machine I'm running is a 6-core processor, you'll see all 6 cores light up, and it can run it through that much quicker than in the days when you only had 1 core. So that's enough for today.